This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Is it alright if we take up a few minutes, mate?
Oh, sure.
Yeah, great. Can I plug a laptop in? Is that alright? We'll show some slides.
Yeah, just connect your laptop, yes.
We're on. You good for us to go? We're recording, so yeah.
It's okay. You can just go inside a few words.
Yeah, right. Hello? Can you hear me up the back there? Anyone? Am I on? Hello?
Yeah, it should be working.
I was just talking about the left turn mic will pick me up. Yeah, that's better. All right. Hi, everyone. We'll just take up a few minutes of your time real quick. Welcome to Solids. My name is Brad, and this is Joel, and we're from MUR Motorsports. So, yeah, just a quick presentation to start you off today. Yeah.
This is our team, 50 senior students and nearly 40 junior students. And those are two cars. The one on the left of you is our combustion car, and the one on the right is the electric car. But next year, we are going to build an autonomous driverless car, which is pretty cool, which means we need more students than ever, particularly electrical students, mechatronic students, software students. Exciting new frontier, and it's a possible capstone project. So if you guys want to work even in the mechanical side of the car, if you guys want to work on something like that, that would look great on your resume.
Yeah, cool. So as Joel mentioned, the change up of the teams, the mix up of the team, is changing a bit. We've got, in the past we've been seen as more of a mechanical team, but we're really moving towards software and electronics. And there's probably a mix of students in here today, so hopefully this interests some of you. And we'd love to have you in now because we're not just a capstone team, we're a racing team as well, which means junior experience is really vital. And we kind of get you in now and give you a bit of experience before handing you more responsibility next year. And then we can find that perfect fit as a role for your capstone. So the next step is to apply if you're interested. We'll be at Open Day just outside House of Cards. We're also your classmates scattered in amongst everyone, so come and talk to any of us if you have any questions. And we do have an application link on our website there, and somebody will look at that and be in touch with us shortly. Thanks, everyone.
Good morning, everyone. So today is the third lecture in FEA. So if you remember from the previous lecture, we learned about the different types of elements and how to derive linear shape functions. And then we learned a little bit about the matrix notation. So the last slide that I showed you last week was this slide. It was about the element stiffness matrix and global stiffness matrix. So the element stiffness matrix is shown by little k, and capital K is for the global stiffness matrix. I put a point here, like in the green, that the size of the K matrix is showing the number of the nodes. This is not really general, so I want to add another point to this. So whenever we have only 1 degree of freedom per each node, this statement is true. So the size of the global matrix or even the element matrix equals to the number of the total number of nodes or the total number of the nodes of that specific element. In other words, if the degree of freedom is more than 1 for each node, then you need to multiply the degree of freedom for each node to the total number of the nodes, and then that would be the size of the total K matrix. For example, so we have an element with 2 nodes. Each node has 1 degree of freedom, right? So it means that the total K matrix would be 2 by 2. But if each node has more than, has 3 degrees of freedom, then the K matrix would be 6 by 6, right? It would be the total number of the degrees of freedom. So I'm going to explain it more like in the examples, but I'm going to update this slide after today's lecture. Right, so going to the today's lecture. So what we're going to learn today is we're going to solve a simple problem using FEA and learn how to assemble the global sniff and nodal force matrices. So this is to just remind you about the 8 steps of going through FEA to solve an equation. So as you remember, in the last session, we talked about step 1, step 2, and step 3. Step 1 was about the discretization and choosing the appropriate element type. Step 2 was the deriving a displacement function, which was basically showing the shape functions. It could be linear or it could be a quadratic function. And the third step is about the relationships between the strain displacement and stress and strain. So these relationships can be obtained from the material. So it depends on the material that we want to choose for that element or for the whole body of the structure. So today we're going to go to the step 4, 5, and 6, deriving the element stiffness matrix, how to assemble the element equations to obtain the global and total equations, and finally introduce the boundary conditions to solve the unknown displacements in step 6 and solve for the element strain and stress for reporting results after solving the equation. So similar to the Hooke's law, within each element or the total structure of the body that we want to analyze, this relationship should be satisfied. F equals to KD. F is the force, like a force nodal matrix. K is the global K matrix or global stiffness matrix. And D is the matrix of displacement, nodal displacement matrix. So just keep this relationship in mind. We're going to use it over and over. And if I want to expand it in the matrix form, it would be like this. So again, if you look at the force matrix, the first subscript is showing the node number that the force is applying on, and the second subscript is showing the direction of the force. So F1x means that the force applying on node number 1 in direction x. And the same for F1y and the other node. And if you look at the displacement matrix, U1 is showing the x displacement for node number 1. V1 is showing the y displacement for node number 1. And W is for the displacement in z direction. So we start an example with this is the simplest example that we can come up with. So imagine that we want to analyze a linear spring. So we want to start with only one element. So we assume that the whole spring is one element, right? So these are the assumptions that we want to make. So the spring is linear, and we are applying two tensions on the two ends of the spring, which are equal to T. So we label each ends of the spring as one node. So the first end is node number 1, and the second end is node number 2. Since we're only having the axial force, like the tension in x direction, we only consider the x displacement for these two nodes. In other words, we only have 2 degrees of freedom for this single element, U1 and U2. Displacement for node number 1 and node number 2. And the other thing is, the initial length of the element is L before applying any deformation to the spring. And based on the material property, or spring constant, is K. So that was the first step. It was discretization and selecting the element type. We discretized the spring as only one element. We use the linear spring element with the K matrix of K. Now the second step is choosing a linear displacement function. So since it's linear, we can just assume that, in general form, U displacement for all the nodes sitting on the spring equals to A1 plus A2x. A1 and A2 are unknowns, and we want to calculate them pretty much the same as the way that we derived the linear shape functions last week. So here, since we only have 2 degrees of freedom, then we only have 2 unknown coefficients, A1 and A2. So now we want to, is it on? Yeah. We want to derive, we want to find out the A1 and A2 for the displacement function. So I'm going to switch to the document camera. So U, which is a function of the x, equals to A1 plus A2x. So this is node number 1, node number 2, and this is U1, and this is U2. U1 and U2 are the nodal displacement. It means that the displacement at node number 1 and node number 2. So since the whole thing is only one element, to make the equations and calculations simple, I'm going to put the origin of the coordinates onto the node number 1, right? So this is the origin of the coordinate. So which means that at x equals to x1, which is basically 0 here, u1 would be a1. I'm just applying the boundary conditions here. And for node number 2, at x equals to x2, u2 equals to a1 plus a2 L. Right? So assuming that the origin of the coordinate is on the node number 1, then x1 would be 0, and x2 would be the length of the spring, which is L. And from this, so if I substitute A1 with U1, then A2 would be U2 minus U1 over L. So we found the coefficients A1 and A2. So now I want to write it down in matrix form. So U would be the multiplication of a row matrix and a column matrix. You can call each term of this matrix N1 and N2. So N1 and N2 are basically shape functions. Very similar to the linear shape functions that we found in the previous lecture. Any question about the derivation? All right. So going back to the slides, so all the calculations and derivations are on the slides. This is how we did it. We applied the boundary conditions, and then we found the A1 and A2 in terms of the nodal displacements U1 and U2. And then we call these two terms N1 and N2 shape functions or interpolation functions. So the third step is now just defining the S-ray and displacement and the relationship between S-res and S-ray. So this is based on the material that we're using here and the equations that there should be satisfied. So it's a linear spring. We all know that the deformation in the linear spring is proportional to the tensile force that we apply onto the spring, right? So just remind yourself, what was the general formula for FEA? F equals to KD, right? F was force, K was K matrix, and D was the displacement. So the reason that we need to use S-strain displacement and then S-stress S-strain is to find the relationship between the force and displacement here, and then derive the K matrix, right? But the good point about the K matrix, about the spring element is we can just find that very easily without just calculating the strain, right? We know that this is the deformation, U2 minus U1, and we know that the tension is proportional to the spring constant and the deformation of the spring. In other words, T, which is the applied forces onto the two nodes of two ends of the spring, equals to K times U2 minus U1. So basically here, we didn't need to go for calculating the S-strain, right? Because we found the relationship between force and displacement directly. So it made it much easier. Right. So I'm going back to the document camera again to derive these equations. This is node number 1, node number 2. This is the external forces. And this is the displacement at each node. So the way that I want to calculate the K matrix for this spring is just deriving all the equations that need to be satisfied, like the equilibrium equations on the spring. So it means that I want to draw the free body diagram for each node and the element. So we have three components here, right? Two nodes and the spring. So if I only look at the spring, these are the internal forces applying onto the spring, which are basically coming from the nodes. And then if I do the same for node 1, this is node 1, so we have an external force here, which is T, and one internal forces from a spring, which is basically opposing the movement of the node 1 with force T. The reason that the direction F1x here is to the right, this is, I just assume all the internal forces on the element is acting like in positive direction to the right. Then I apply the reaction of that onto the node, right? This is the third Newton's law. And And for the second node, again, apply the reaction of F2x, little F2x, and the external force. So what we found from here is, from this node number 1 is, we know that sigma fx should be 0. And then t equals to minus f1x. And for this one, if we apply the equilibrium, all the forces should be in equilibrium, then t would be f2x. And what we just found about the relationship between the external force and deformation of the spring was T equals to K U2 minus U1, right? So now what I want to do here is I want to find out F1x and F2x in terms of the U1 and U2. So this would tell me that F1x is U1 minus U2, and F2x is exactly equal to T, K, U2 minus U1. And from these two equations, I want to write it down in matrix form. So it would be the force nodal matrix So we call this matrix local stiffness right? So what we did here is we knew that the external applied tension was proportional to the deformed length of the spring and the spring constant, T equals to K times U2 minus U1. And then to find out the nodal, the force nodal, which are acting onto each node, F1x and F2x, we drew the free body diagram for each node and the spring, and then find out the relationship between the external force and the internal forces, F1x and F2x. And then write down these two equations, F1x and F2x, in terms of U1 and U2 in matrix form. And this is the K matrix. So we have two nodes here. Each node has 1 degree of freedom. In total, we have 2 degrees of freedom. That's why the K matrix here is 2 by 2. Any questions? Yes?
We don't have apply the external force on the spring?
Can you say it again?
Don't we apply the external force on the spring?
In the free body diagram, you mean?
Yes.
On the spring, you said?
Yeah.
The external T?
Yes.
So these are the things that we have. We have two nodes, like like 2 points. They attach to the spring, and we apply the external force onto the 2 points, not onto the spring directly. Right? Yeah. That's why it doesn't show up in the free body diagram for the spring. But we can see it in the onto the both nodes. Yeah. It's like a handle. I mean, we have 2 handles, and the spring is connected to the 2 handles. So we're pulling out the 2 handles, basically applying the forces, I would say, indirectly to the spring. Any other question? All right. So this is how we did it, how we found the element stiffness matrix. It's very easy, like a K minus K minus K and K. And so now we found the element stiffness matrix. Now we need to go for global stiffness matrix. But the good thing here is, since we only have one element here, the local stiffness matrix equals to the global K matrix. And the same for the force matrix. So small k, little k equals to capital K, and little f matrix equals to the capital F. So this was a general example. So if we know the external forces, then we can easily find the displacement U1 and U2 based on those 2 equations, or in the matrix form. And if we want to find the displacement, I mean, as I said, we need to apply the boundary conditions. The boundary conditions here is the external force. So we replace like F1x with minus t and F2x by t, and U1 and U2 can be calculated. So now, what if that we have more than one element? This is the, I mean, that one was very easy. It was good to how to drive the K matrix for each individual element. But the thing is, what if we have more than one element, which in 100% of the cases we have more than at least 2 or 3 elements. So this is an example here. So this time, we connected 2 springs together with the 2 different K matrix. So one of, the first end of the first spring is fixed, and we're applying 2 external forces, F2x and F3x, on node number 2 and 3, right? So we have 2 elements here. How many nodes we do have here? 3 nodes. So which means that, assuming that we're only having x displacement, how many degrees of freedom we have in total? 3. Again, it means that the global K matrix should be the size of 3 by 3, exactly. But we just learned in the previous example that the K matrix for each individual element was 2 by 2, right? So now we need to find out a way to combine the 2 individual element K matrix for spring 1 and for spring 2, and then create the global K matrix, which is a 3 by 3. So if you have noticed here that I haven't put the node numbers in order. I mean, you could have, it's totally up to you. There is no like rule for that, but I just put like randomly here to like make it like a little bit challenging for you. All right, stiffness of the spring elements 1 and 2 are K1 and K2, and we're applying axial forces F3x on node number 3 and F2x on node number 2. And the other thing that you need to pay attention is whenever we have more than one element and you want to assemble the global matrix, the first thing to do is just find out the common nodes. So here we have two nodes. They connected to each other through one node, which is node number 3. So just remember that. That one is the tricky node here. Right. So based on the element stiffness matrix that we've derived, we can just write it down again for each individual element here. It's the same. It doesn't change for any of them. But just be careful about the subscript and superscript. So for example, in node number 1, it was node number 1, for spring number 1, element number 1, we have two nodes, node number 1 and node number 3. So that's why in the first like equation, you can see F1x, F3x, right? And the superscript is showing the element number. So this is important. Don't get it confused. The superscript is showing the element number. The subscript is showing the node number. And for element number 2, we know that the end nodes are node number 2 and 3. That's why we have 2 and 3 in the superscript. In subscripts. And the superscript for all of them are 2. So if you want to use the same method that I use for deriving the element K-matrix, which was driving down the equilibrium equations for nodes and for a spring, we need to make sure that the displacement of node number 3 that we can calculate from element 1 and element 2 should be the same. This is the continuity rule or compatibility requirement. It doesn't matter from each element you're calculating the displacement for node number 3. Since it's a common node, you should get the same answer. All right. So if you want to use the free body diagram, we have 3 nodes and 2 elements. So we can just break down all these 5 components and then just do exactly how I did for the one individual element. So here we can see that if you look at the node number 3, capital F3x should be equal to the summation of the little f3x for element 1 and f3x for element number 2. This is the equilibrium equation at node number 3. And if you look at the node number 1 and 2, these equations should be satisfied. So F1x, capital F1x, is the reaction force at the fixed end. We don't know it, right? We only know that the displacement is 0 there. So then we just substitute the little f3x and little f3x for element 1 and element 2, and then we can find out the equation for capital F3x in terms of U1, U3, and U3 and U2 from the both elements. And the same for F2x and F1x. So now we have three equations in terms of all the nodal displacements U1, U2, U3. Now we can find out the global K matrix, which is this. I just wrote it down in matrix form from those three equations in the previous slides. But this sounds too difficult, right? Just chucking the elements and nodes and satisfy the equilibrium equations. It's really time consuming. Fortunately, there is another way to do this, which is called the direct stiffness method. So this is how it works. We do have two elements, and we know the K matrix for each of the elements, right? For element number 1, it's K1 minus K1 minus K1, K1, and the same for spring number 2. I think it's better to write it down. So for element number 1, the little K matrix was So the reason that I wrote it down first in K1, K13, K31, and K33 is showing you that what nodes are located at ends of this element. Node number 1 and node number 3. And if I do the same for element 2, three, 3, 2, and K. So now the direct stiffness method is saying that if you want to directly find the global matrix from the element stiffness matrix, this is how you can do it. So first of all, just estimate the size of the global K matrix. We have 3 degrees of freedom, so the global K matrix is 3 by 3, right? So this is the global K matrix. It's 3 by 3. This time, for writing down the global K matrix, I put the numbers in order. So if I put node here, this is showing 1 related to node number 1, related to node number 3, and the same for the rows. So these are not coefficients, right? Don't get confused for that. This is just showing it's like a guideline to interpret what does each component in global matrix mean. So for node number 1, definitely it's K11, right? Where do we have K11 from these two elements? It's only here, right? So I'm going to put K1 here. So let's just put all these 4 components into the global matrix. So we have K11 is K1, K13, minus K1, K31, minus K1, and K33 is K1. All right. K13 is minus K1, K31 is minus K1, and K33 is K1. Right? And now I want to do the same for element node number 2. We have these 4 components. I want to disperse all these 4 components into the global matrix. We have 3 by 3, 3, 2, 3, 3, 3, 2, 2, 3, and 2, 2. So this is K22. It's K2. K32 is minus K2. This is minus K2. And this is the tricky point here. So as you notice that in all these 8 components in total for K matrix for element 1 and element 2, there is only one common component, right? Which is K33. This is where you need to add up these 2 components and put it in the global matrix. So here should be add up to K2 as well. And if you don't have any value for the rest of the components in the K matrix, just put 0 there. So can anyone tell me that what does it mean to have 0 values for some of the components in the global K matrix? So for example here, we know that for components K12, it's 0. Exactly. So if you just look at the problem, this is node number 1, 3, and 2. Node numbers 1 and 2 are not connected to each other directly. Right? So that's why it's 0. That's why the corresponding components in global K matrix is 0. All right, so this is the way to do it. Just be careful that the order that you put for the K matrix, like 1, 2, 3, it should be the same for the displacement matrix and force matrix. Any questions about the direct global matrix? Yes? K1 plus K2, this there? No, why it should be 0? No. You got it? No. Right, so, yeah, so this is the global stiffness matrix for these 2 spring elements. And now we want to apply boundary conditions. There are a couple of things left. I'm going to just say it quickly. So we have a couple of boundary conditions here. The first thing is node number 1 is fixed. What does it mean? The displacement at node number 1 should be 0. So if we if I want to say it in mathematics, u1 equals to 0, right? So in the equation f equals to kd, the general formula for FEA, we put u1 as 0. And then the rest of the equations can be just expanded and find out f2x and f3x. And if we know the external forces at node number 2 and 3, which are the capital F2x and F3x, it's very easy to find out the displacements at node number 2 and 3. So this is just like mathematics. So we know that when we have like this equation, matrices, the multiplication of A, B equals to C. If we want to find out B, we need to calculate the inverse of matrix A. So here we need to calculate the inverse of K matrix. And if you do that, this would be the nodal displacement in terms of the F2x and F3x. And once we got U2 and U3, it's very easy to go back to the first equation here, F1x, and then calculate the reaction force at the fixed end based on the U3. So this is a very nice homework for you guys. Try to practice it at home. Hopefully, I'm going to go through it next week before the mid-semester exam. But try to solve it yourself and drive all the equations that I did here at home to just make it easier to understand and just learn the concepts of the global metrics and how to apply the boundary conditions. Any questions? All right, thank you so much. I'll see you next lecture.
It's very interesting. I cannot log out. I've never seen that. Let's do a restart. Yeah, like maybe let's do like this. I'm gonna restart it. You don't need that, right?
I will, but if we restart,
Is it
it'll
okay?
be ready just in time, so that's all right.
Yeah. Oh jeez, I cannot even restart it. Just use my login, my account. I know what's the problem. Oh,
When in doubt. Shut down your computer now. Restart. Really? Click Microsoft. Really? That's ridiculous.
Oh, you got it? Oh.